This video is the demonstration of behavior or the analysis of hyperelastic material. Hyperelastic material is a material which behaves or which responds elastically for large strains. I repeat, hyperelastic material is a material which behaves or responds elastically for large strains. In this example, you can consider a body which is moving in the x direction. The shape of the body is circular initially, and it is forced to move in the x direction through a smaller cross-sectional area. The body is compressing itself and flowing through the small cross-sectional area without undergoing a permanent or the plastic deformation, which means the shape before the deformation or the shape before it is being passed through the smaller cross-section is same as the shape after passing through the smaller cross-section. That's the reason why this material is called as hyperelastic material. This behavior can be observed for a material like rubber. To model this behavior, there are different material models. One of the material model to model such a behavior is Mooney Rivlin material model. Let us understand how to define the parameters of Mooney Rivlin in ANSYS Workbench to predict the behavior of hyperelasticity for the materials. Create a new static structural analysis file. Rename the file to hyperelastic. Enter. Pick on the engineering data, right-click, press hold, pick on Edit. A default material can be seen in the engineering data, that is steel. Let us remove this material from this analysis because this material is of not interest. Pick on the engineering data source. Under the engineering data source, browse for the hyperelastic materials. Under hyperelastic materials, we have elastomer sample Mooney Rivlin. Pick on that material, pick on Add. This material will be added to the engineering data for our analysis. Pick on engineering data source again. You can observe under the elastomer sample Mooney Rivlin, a stress strain data is available. Using this stress strain data, we need to derive the parameters or the Mooney Rivlin parameters required for the analysis. This stress strain data is uniaxial tension test data or uniaxial test data. Pick on the hyperelastic and pick on Mooney Rivlin 5 parameter. Drag this Mooney Rivlin 5 parameter on the uniaxial test data and place it. You can observe the Mooney Rivlin parameters are undefined. They are material constant C10, C01, C20, C11, C02 and incompressibility parameter. Pick on the curve fitting. Right-click, press hold. Pick on Solve Curve Fit. Once the curve fit is been solved, the values are calculated. These calculated values are to be copied to the Mooney Rivlin 5 parameters. Hence, right-click on the curve fitting again, pick on Copy Calculated Values to Property. It can be observed that all the parameters required for the Mooney Rivlin material model are now defined. Let us browse for one more engineering material, that is polyethylene. Pick on the engineering data source again. Under General Materials, browse for the polyethylene material. Press the Add button. Now pick on the engineering data source button again. Once elastomer sample material and polyethylene material are loaded in the project, pick on Return to Project. At this point of time, we have defined two materials. Now, let us import a geometry into the ANSYS. Pick on the geometry. We are going to conduct a 2D plane strain analysis, which means we are going to simplify a 3D problem into a simple 2D plane strain analysis for simplicity and to reduce the computation time. Pick on Analysis Type as 2D. Right-click on the geometry and browse for the geometry. Pick on the Import. The geometry is already in the temporary memory. Pick on this geometry. You can observe a tick mark or a check mark which represents the material is loaded. Right-click on the geometry. Pick on Edit Geometry. Ensure that the unit of ANSYS Workbench is millimeter. Pick on OK. It can be observed that the geometry is loaded but is not updated. Set few of the parameters for the import geometry. Keep the operation as Add Material. Solid bodies import, yes. Surface bodies import, no. Line bodies import, no. Once these parameters are set, pick the analysis type as 3D. We are setting it as 3D just to import a 3D model. Then we are going to convert it into a 2D model. Once these import details are defined, pick on Generate button at the top left corner. You can observe generating the feature. The geometry is now imported. In this case, we are going to fix the top and the bottom dies. They are made up of polyethylene material, and center part, which is made up of the hyperelastic material, will be stretched and made to pass through the small cross-sectional area. To convert this 3D problem into a 2D problem, make sure that the mid-surface is extracted. Pick on Tools. Pick on Mid-surface. Pick on the front face and the back face by pressing hold Ctrl button. Pick on Apply. Pick on Generate. Similarly, extract the mid-surface for the hyperelastic component. Tools, Mid-surface. Pick on the front face, press hold Ctrl, back face. Pick on Apply, pick on Generate. Similarly, for the third component, pick on the face, with Ctrl press hold, press on the other face, apply, generate. Right click, press hold, pick on the view and pick on the front view. This is a 2D model. This model needs to be imported into the mechanical now. Go back to the project page. Pick on the model, right click and pick on Edit. Mechanical is starting now. Observe the left bottom corner. The attach status is completed. We need to define what kind of analysis is this. Pick on the geometry and select here as this model is plane strain analysis. Under the geometry, since we have defined two different materials, the materials are not automatically assigned. The first part, let us see which part is that, and the second part should be made up of polyethylene material. The hyperelastic part should be made up of Mooney Rivlin or elastomer sample material. There is no connection existing between the parts. Let us define the connections. Right-click, insert, pick on the manual contact region. The contact has to happen for the hyperelastic body and the top die, and hyperelastic body and the bottom die. Pick on, orient the view to front. Under the contacts, pick on the first contact. Under the contact, pick on the edges. Ensure that the edges is selected. The first edge, second edge. Pick on all the edges of the model. Pick on Apply. Under the target, pick on the edges of the top die. Pick on Apply. Similarly, create one more contact. That can be done by creating the duplicate of this contact. Pick on Duplicate. Under the second contact, ensure that the contacting body is going to remain the same. Hence, only target edges will be changing. Under the target edges, pick on the bottom die edges. Pick on Apply. Ensure that the target and the contact edges are now selected. but there should happen a friction behavior between the parts. Therefore, pick on both of the contacts by pressing hold Ctrl. Change its definition type to frictional contact. Enter the frictional coefficient as 0.2 or 0.14. Under the behavior, change it to a symmetric behavior of the contact. Under the advanced, select the formulation to the pure penalty approach. Under the detection method, use as node normal to target. Under the interface treatment, add offset no ramping is selected. Under the normal stiffness, enter a manual stiffness of 0.1. That is a normal stiffness factor. Update the stiffness for each iteration. Enter the pinball region radius as 2. Once all these contact parameters are defined, let us proceed for updating or creating the mesh. Right-click on the mesh, insert, pick on the refinement. For refinement, select 3 surfaces. Ensure that the face is selected. First face, press hold Ctrl. Second face, press hold Ctrl. Third face, pick on apply. Observe under geometry, 3 faces are selected for the mesh refinement. Pick on the first body, right-click, pick on generate mesh on the selected bodies. Similarly, pick on the second body, right-click, pick on generate mesh on the selected bodies. Similarly, pick on the third body, right-click, pick on generate mesh on the selected bodies. Once the meshing is completed, pick on the mesh. Observe the elements. We have made a refinement at the contacting area. Let us proceed for defining the loads and boundary conditions. Here, a load means a displacement for the hyperelastic body in the positive x direction. Pick on static structural, right-click, insert, pick on displacement. Pick on the edge, pick on the backside edge, pick on apply. It should displace in the x direction only to a magnitude of 33 millimeters, and it should not move in the y component, hence make it as a constant 0 value. Right-click on the static structural, pick on insert, pick on fixed support. Pick on the edges, select the top edge and pick on the bottom edge. These edges need to be fixed in all degrees of freedom. Once the required boundary conditions and the load is defined, let us proceed for defining some of the analysis settings. Hence, pick on the analysis settings here. Under the automatic time stepping, pick on and enter the initial sub-steps as 100. Enter the minimum steps as 50. Enter the maximum steps as 1000. Select the solver type to be a direct solver. Select the weak spring to be off. Enter the large deflection as on. Under the output controls, pick on the nodal forces to be yes. Once the necessary analysis settings are done, retrieve for the results. Right-click on the solution, insert, pick on the deformation, pick on total. Right-click on the solution, insert, pick on the stress, pick on the first principal stress or the maximum principal. Right-click on the solution, insert, pick on the strain, pick on the equivalent or von Mises strain. Right-click on the solution, pick on solve. The solution process is now started. You can observe the overall progress. Pick on the solution information for the detailed history of what the solution is going on. Pick on force convergence to look for the convergence graph. Now 35% or 39% of solution is complete, 41%, 43%. It will take a few minutes of time to converge the solution fully. Once the solution is completed for complete 1 second, let us proceed for post-processing the results. Pick on total deformation. This is how the model has deformed. You can observe the behavior in the animation mode. Pick on the graph. Enter the number of frames as 100 frames and simulation time or the animation time for 10 seconds. Pick on animate. You can observe the behavior of this hyper-elastic material. Not all the materials will have such kind of behavior. You can observe the material is going to regain its shape and size even after a large strain. This behavior is hyperelastic, and this material model is called as Mooney Rivlin material model, and the parameters required for this material behavior are defined before the solution process or the analysis process. For any communication or contact, please write me on engineeringtutorsdesk@gmail.com. Thank you for watching this video. If you like this video, please share with your friends. Please subscribe my channel for more videos. Please press like button if this video has helped you.